Now that we've discussed minerals and rocks, let's start talking about the Earth's interior. And so the way that we have actually learned about the Earth's interior is through seismic waves. Seismic waves are caused by earthquakes. And so because of tectonics, the motion of the crusts of the Earth, they will get these sudden breaks, which release energy, which causes the seismic wave to travel through the Earth. If you're in one of these regions that feels the vibration, that's what we experience as earthquakes. So we actually use seismic waves to help us understand what's going on in the Earth's interior because we can't actually get down there. But seismic waves will travel through the Earth. Okay, so there are two overarching types of waves. There are body waves, which actually travel through the volume of the Earth. They actually get through the entire Earth. Okay, and then there are surface waves. Surface waves only travel along the surface, so they don't actually tell us about what's happening inside of the Earth. Okay, body waves, we have two types of body waves. There are primary waves, also known as P waves, and secondary waves known as S waves. Okay, surface waves also have two types. There's Rayleigh waves and Love waves. Okay, so primary waves, these are one of the volumetric or body waves. These are longitudinal. So if you remember way back when talking about waves, these are the ones like a slinky where we compress and then stretch. So these are longitudinal. They compress and expand the material as they move through. The compression and expansion is parallel to the wave's direction. Primary waves are able to travel through any state of matter. As long as there's a material there, primary waves are able to travel through it, just like longitudinal waves. Now, the reason why we refer to these as primary waves is because they are the fastest. They're the first ones to arrive after an earthquake. So primary waves are the fastest, and they can travel through all different types of material. The other type of body wave is the secondary wave. These ones are transverse. So in other words, as the wave moves one direction, the material moves perpendicular. So these vibrate rock up and down as or side to side as the wave travels through. So the motion is perpendicular. Now, secondary waves can only travel through solids. These cannot go through liquids or gases. They can only travel through solids. And this is because only a solid has a strong bond so that as one piece goes up, it's able to drag the next piece up with it. So liquids are able to block secondary waves. Now, the reason why we refer to them as secondary is because they are slower. They arrive second. So first the P waves hit, and then the S waves hit. So the surface waves are actually the slowest of all of the different types of waves. They're the ones that arrive last and are actually recorded last. Rayleigh waves have a rolling type motion, similar to what you see with ocean waves. So they are similar to ocean wave movement, kind of this back and forth, up and down motion. So the ground actually moves up and down. Love waves have a similar motion to the S waves. These are also transverse. However, it's side-to-side, back and forth motion. It's almost whip-like. So both the Rayleigh and Love waves are actually very destructive because they're right up on the surface, whereas the body waves travel through the volume of the Earth and don't affect the surface as much. Here's our first lecture quiz question. The most destructive earthquakes are caused by the passage of surface waves because A, they travel faster than other seismic waves, B, they occur in the crust, the densest layer of the Earth, C, they occur at the surface where the ground shakes up and down and from side to side, or D, they travel deep in the Earth's interior. Go ahead and think about it, and we'll discuss it in a second. All right, so I actually gave the answer away just a little bit ago. It is C, because they happen on the surface where the ground that we build buildings on is shaking up and down and from side to side. This is why they're the most destructive. Okay, so the correct answer is C. Okay, so the way that we actually use seismic waves to tell us about the interior is because of refraction. If you remember back when we're talking about waves, refraction is where a wave suddenly changes direction because of a change in speed. Okay, so an abrupt change in the seismic wave's speed will lead to a bending, and that can then be used to figure out different densities. Okay, so the way that this actually works, so on this top diagram, we're looking at a cutaway of the Earth, looking at P waves. Okay, so we actually have the earthquake up here. In this case, it's at the North Pole for convenience. As the waves pass through, they will move and then arrive somewhere else on the surface of the Earth. Okay, so this line right here had no density change, or at least very little, so it went straight through. However, the line right next to it had a sudden abrupt change in velocity of density, which caused it to refract and move in a different direction, and then it hits another change in density and bends again. Okay, so we have these two waves that started out right next to each other up here, but then end up at very different positions because of refraction. This region through here where we do not detect the wave, this is what is known as a shadow zone. Okay, so for the P waves, we actually get this donut-shaped shadow zone. Okay, so we experience the seismic wave through this region, then it's missing through here, and then we pick it up again towards the opposite side of the Earth. Okay, so we get this donut region where we don't experience the seismic wave. So what we do, we don't actually know how the wave traveled through the Earth, but we do know where it's hitting on the surface. So we look at the shadow zone and then trace back, saying where did the waves have to refract to cause this shadow zone? Okay, so that's how we use the P waves. Okay, with the S waves, we actually get a giant shadow zone. So in this bottom image, the white lines are the S waves, and we experience S waves to the top half of the Earth, but then we get no S waves through the bottom half of the Earth. Okay, that means that something in the interior has to be blocking the S waves. Well, the only thing that can block an S wave is a different state of matter. Remember, S waves can only go through solids, so this shadow zone is showing us there has to be a liquid portion within the interior of the Earth. Okay, so using this seismic wave information, we get the idea of that the interior of the Earth is actually layered. Okay, at the very center, we have the inner core. Surrounding that is the outer core, then the mantle, and then we have a relatively thin crust at the very surface. Now, the core itself is predominantly made of metallic iron. Okay, so the core is iron. Now, that is true for both the inner core and the outer core. What causes the difference between the inner core and the outer core? The inner core is actually solid. Okay, so the inner core is solid, and the outer core is liquid. Okay, now, if you remember back, last time we talked about how the deeper you go into the Earth, the hotter it gets. What this means is that the inner core is actually hotter than the outer core. Okay, and yet, the inner core, even though it's hotter, is still a solid, whereas the outer core, even though it's cooler, is a liquid. Okay, the reason for this is pressure. Remember, if something's a solid, liquid, or gas, it's based off of not just temperature, but also pressure. So because of all of that other stuff pressing down onto the core, the inner core is a solid because of the intense pressure, and then the pressure is just less enough through the outer core that it's able to be a liquid. Okay, so both the inner core and outer core are iron. The inner core is solid. The outer core is liquid. And because it is liquid, it's actually possible for the outer core to flow. Specifically, it has convection. If you remember talking about convection previously, and it is the liquid outer core that actually generates the Earth's magnetic field. Hey, here is our second question. The shadow zone in S waves shows A, distinct layers between the crust and mantle, B, there is a liquid part of the core, C, distinct layers between the inner and outer core, or D, the region of maximum displacement? Go ahead and think about it, and we'll discuss it in just a second. All right, so the answer is B. Hey, remember, S waves can only travel through solids. Okay, so we get this huge section on the surface of the Earth where we do not experience S waves. That means the S waves are being blocked, and the only way to block an S wave is if there's a large liquid portion. Okay, so this indicates there is a liquid part of the core.